All right, let's get into it. Today, we are cracking the code of organic chemistry. Think of it as the language that literally describes the building blocks of life. I mean, have you ever wondered how in the world chemists keep track of millions, literally millions, of different molecules? It sounds kind of impossible, right? But the secret is this really elegant system. It's basically a language with its own alphabet, its own shorthand, and yeah, its own grammar.
And that's exactly how we're going to tackle it today, like we're learning a new language. First, we'll get to know the alphabet, the atoms. Then we'll figure out the shorthand, how chemists actually draw these things. And then the really fun part, the grammar. These are the rules for how you put it all together to build their names.
So here's the game plan. We'll start with the star of the show, carbon. Then we'll get into drawing the molecules, we'll cover the basic naming rules, then move on to naming chains with branches. And finally, we'll see how it all expands beyond just simple chains. Sound good? Let's jump in. All right, first up, carbon. This is the absolute superstar of the periodic table, the very heart of this new language we're learning. So what are we even talking about when we say organic chemistry? Well, it's pretty simple, really. It's the field that studies any compound that has a carbon skeleton. You can think of carbon as the backbone for, well, almost all the molecules that make up life as we know it. But that begs the question, right? Why carbon? I mean, what is it about this one element that gives it this amazing ability to create this incredible variety of molecules? Okay, it really boils down to two key superpowers. The first one is called tetracovalency. It's a bit of a mouthful, I know, but all it means is that carbon can form 4 bonds. It has like 4 hands to connect with other atoms. And the second superpower? Catenation. This is its amazing talent for linking up with itself, with other carbon atoms, to form these long chains, branches, even rings. It's like a molecular Lego set. And these two properties, that's what makes carbon the ultimate building block. Okay, so before we can start naming these things, we have to know how to draw them, how to write them down. And just like any language, there's the really formal, long-winded way to write something, and then there's the expert's shorthand. So let's take this molecule here, pentane. You could draw it out the long way, like this. See how you've got every single carbon, every single hydrogen, and every single bond all shown? It's super clear for sure, but you can probably see how this would get really cluttered really fast with bigger molecules. So, to clean things up and save some space, chemists came up with the condensed formula. All we're doing here is grouping the hydrogens with the carbon they're attached to. So instead of drawing out all those little lines for the bonds, you just write CH3, then CH2, CH2. You get the idea. It's just so much cleaner. But now, this is the real expert's code. This is the bond line structure, and it is honestly a minimalist masterpiece. It looks simple, right? Here's how it works. Every point and every end of a line, that's a carbon atom. The lines themselves, those are the bonds. So you're probably asking, where are all the hydrogens? Well, they're kind of invisible, but they're there. See, chemists just know that carbon always forms 4 bonds. So they just assume the hydrogens are there, filling in any empty spots. It is by far the fastest and cleanest way to draw a molecule. This is the gold standard you'll see everywhere. Okay, nice. We can now read the shorthand. So that means it's time to learn the actual vocabulary. Let's move on to the basic naming rules. So for these simple straight chain molecules, we call them alkanes. The name comes down to just one thing: how many carbons are in the chain. That's it. So 1 carbon, that's methane. 2 carbons, ethane. 3 is propane, 4 is butane. After that, it gets even easier, because it just uses the Greek prefixes you probably already know. 5 is pentane, 6 is hexane, 7 is heptane. You see the pattern. This table right here, this is basically our dictionary. But, of course, life isn't always that simple, right? Molecules aren't always just nice, straight lines. Nope, they have branches coming off them. And this is where we really have to learn the grammar. Okay, rule number 1, and this is the most important rule of all, so listen up. You have to find the longest continuous chain of carbons in the molecule. Now notice I said continuous, not straight. It can twist and turn as long as you don't lift your pen. Just look at this example here. If you trace it out, the longest path you can find that's all carbons connected together is 6 carbons long. So the last name of this molecule is going to be hexane. That main chain is called the parent chain, and everything else that's sticking off of it, that's what we call a branch or a substituent. Right, on to rule number 2. This one's all about giving those branches an address. So what you do is you number the carbons in that main parent chain. But which way do you start? Simple. You start from the end that's closest to the first branch. The whole goal here is to give those branches the lowest possible address numbers. This molecule is a perfect example of that. Okay, so the longest chain has 3 carbons, which makes it a propane, right? And it's got a little 1-carbon branch sticking off of it, which we call a methyl group. Now, if we number it, well, whether we start from the left or the right, that methyl group is always going to be on carbon number 2. So its name is 2-methylpropane. That number, the 2, has a fancy name, a locant. It's literally the branch's street address. And finally, rule number 3. This is where we put the whole thing together. You figure out the names of all the branches, methyl for 1 carbon, ethyl for 2, and then you just list them in alphabetical order right before the parent name. Let's look at this one. The parent chain is a hexane, and it has 2 different branches. There's an ethyl group on carbon 3 and a methyl group on carbon 2. Now here's the part that can trip people up. Even though 2 is a lower number than 3, that doesn't matter for the order. You always list them alphabetically. E for ethyl comes before M for methyl. So the correct full name is 3-ethyl 2-methyl hexane. Okay, here's a little pro tip, something that catches a lot of people just starting out. When you're putting things in alphabetical order, you totally ignore prefixes like di for 2 or tri for 3, so the D and T don't count. But, and this is the tricky part, you do count the I in something like isopropyl and the N in neo. Yeah, it's one of those weird grammar rules, but it's a super important one to lock in. So there you have it. Those are the basics. But the really beautiful thing about this whole system, this language, is just how flexible it is. It's designed to expand and handle almost anything. I mean, take a look at these. The exact same rules we just learned can be adapted for molecules with double or even triple bonds. All you do is change the ending of the parent name from ane to ene for a double bond, or ine for a triple bond. And then you just pop a number in to show where that bond is. So a 2-carbon chain like ethane, but with a double bond, it just becomes ethene, see? The core logic stays the same, you just learn a few new vocabulary words. So there you go, you've just learned the fundamentals of a whole new language, the alphabet, the shorthand, and the grammar of organic chemistry. And that's a seriously powerful tool for understanding the molecular world all around us. So now that you know how to speak the language, what molecules are you going to decode next? The world of things like caffeine, plastics, medicines, it's all out there waiting for you to read it.